Good morning. Thank you very much. It's a big opportunity for me to be here. I'm glad to be here today with you. And only to mention that 10 years ago, I was also a high school student, but very far from here. I'm from Spain. And just to say you that I was also in your same situation about decide what to do and what to study. And science is kind of particle physics in more concretely, which is my field, is kind of an exciting, very, very exciting job. You have, it's like a game. You have several pieces, several rules, and you have to construct a puzzle. And I hope you will enjoy a lot today in this discussion between Joe and Rocky. And let's say hello to Rocky, which is going to talk about the quantum and the cosmos. Thank you.
Thank you, Olga. It's a pleasure to be here on this beautiful spring day. And thanks, everyone, for coming out through the snow and slush. As Dr. Marshall mentioned in the introduction, I'm a cosmologist, not a cosmetologist, so there's a confusion that often happens there. The job of a cosmologist is to try to understand the universe. And as soon as we understand everything about the universe, I'm out of a job. But what I want to do is to convince you today that I will be working for a very long time, because there are deep mysteries about the universe. And not only will I be working for a very long time, but I guarantee you there will still be mysteries remaining if you decide to be a cosmologist. Now, cosmology is not a new field. It's always been done. The oldest cultures had cosmology. 4,000 years ago, the cosmology might have been the cosmology of the Egyptians. And a typical question that was asked of cosmologists, what happens to the sun at night? We knew we lived in a flat universe and somehow the sun disappears over the horizon. What happens to it? Well, the Egyptian cosmologists had an answer. They had a cosmological model involving a goddess named Nut. And in this cosmological model, every evening, Nut would swallow the sun, and after a gestation period of 12 hours, she would give birth to the sun the next day. So that was a cosmological model of 4,000 years ago. The cosmological model of 1,000 years ago was very much different than our cosmological model today. There were mysterious things in the sky, and you could see the machinery that moves the heavens. So this is the cosmological model of 1,000 years ago and in the year 2004 in certain places of Georgia. Today's cosmological model is different, of course, and the thing that is a hallmark of today's cosmological model is a connection between the inner space of the quantum and the outer space of the cosmos. So today we perceive a vastness to the universe that would have been unimaginable 1,000 years ago, and in fact would not have been believed even 100 years ago when Leon was in school. We have learned that we cannot understand the largest things in the universe without understanding the smallest things in the universe, and that's the theme of this morning's presentation. This thought was expressed in 1911 by the great American naturalist John Muir, who wrote in his book, My First Summer in the Sierra. He wrote, when we try to pick out anything by itself, we find it hitched to everything else in the universe. Not only is the inner space of the quantum hitched to the outer space of the cosmos, but our conception of our place in space and time, our cosmology, is hitched to everything from art to philosophy. This idea was also expressed in the words of the great American astronomer Carl Sagan, who said, "To make an apple pie from scratch, you first must invent the universe." For some reason, the Carl Sagan cookbook was not a success. His recipe for beef stew started with, "Discover all the laws of physics." So it was not a success, but you get the idea. At departments and universities and high schools, nature is divided into astronomy, physics, chemistry, biology, etc. But nature itself is not so easily divided. And again, the goal today is to give you some appreciation of this connection of the unity of nature, and how to understand the largest things in the universe, you have to understand the smallest things in the universe. So what I would like to do in these opening remarks is to mention two deeply troubling, profound questions we have about the universe today. And it revolves around the simple question of what is the universe made of? Now, the questions in cosmology, and in fact in much of science, are simple, but the answers may not be simple. So let's take a look at what the universe is made of. So if we go to our friends the astronomers and tell them, go out on some distant mountaintop in the middle of the night, freezing, and look through a telescope, what do you see? An astronomer may say that the universe seems to be made of galaxies. Galaxies are enormous structures, I think some of the most beautiful things in nature. Enormous structures consisting of hundreds of billions of stars. And of course, our own star is part of a Milky Way galaxy, the Milky Way galaxy, just one galaxy in a universe with billions and billions of galaxies. So a good answer to the question, what is the universe made of, might be the universe is made of galaxies. So that's a good answer, but it's not a complete answer, because a problem comes when we look at a galaxy in detail. Astronomers and physicists can determine the mass of a galaxy, because a galaxy like this is spinning. The stars are orbiting about the center of the galaxy, just as planets are orbiting about our sun. When we measure how fast the stars are orbiting about the center of the galaxy, we can't understand what's holding the galaxy together. The only force that could prevent the galaxy from flying apart is the force of gravity. But galaxies are spinning so rapidly that the gravitational force produced by the stars that we see is insufficient to hold the galaxy together. So we can determine the mass of the galaxy by seeing how rapidly it rotates, and it seems to be much more mass than we can see in the form of stars. So when you see a picture of a galaxy, you're only looking at the visible universe, and in fact, there is the invisible universe that we don't see. Now, this small accounting irregularity is not so small. There seems to be 50 times more mass associated with the galaxy than we can account for in the form of stars or any other thing that we can see. So there are missing pieces in our picture of the universe, and we can't say the universe only consists of stars and galaxies, because there's 50 times more mass that we don't see. This mass that we don't see, we know it's there because it's exerting a gravitational force, but we know nothing of its nature. It's called dark matter. So this is this is a picture of a galaxy taken by an astronomer, and this is a picture of a galaxy that's produced by a computer. And in this picture of a galaxy, the galaxy that's seen is just this yellow disk in the center. And what's illustrated in this picture, just from a computer, it's not what you see, is what we believe to be the distribution of dark matter. There's much more dark matter associated with the galaxy than there is normal matter in the form of stars, planets, people, and things like that. The structure of a galaxy is something we don't understand. We don't know what most of the mass of the universe consists of. That is problem number one. That's pretty embarrassing if you're asked, what is the universe made of, and you say you don't know. It gets even worse because in the past few years, the idea that in addition to dark matter, there is another component that makes up most of the universe known as dark energy. And the idea of dark energy was first proposed in 1917 by Albert Einstein. In 1905, Einstein developed the theory of relativity, and he proposed that space and time are related. And you shouldn't think of space and time as independent quantities. You should think of a single space-time. In 1915, in his theory of gravity, he realized that space itself is not flat like you learned in geometry in high school, but space can be curved and warped and bent. Then in 1917, he had an even more remarkable idea that empty space itself, space without anything in it, just the fabric of space itself, has a weight, has an intrinsic density to space. He called this the cosmological constant, and today we generalize it as dark energy. Now, the history is, in 1917, Einstein proposed the cosmological constant, but the reason he proposed it is that he believed that the universe was not expanding, and the cosmological constant was something he introduced in order to keep the universe from expanding. Then in 1929, Edwin Hubble discovered, in fact, that the universe is expanding. And in 1934, Einstein called the introduction of the cosmological constant my biggest blunder. And it wasn't until 1998 that astronomers found evidence that indeed there is a cosmological constant. So the lesson here in science is never admit you're wrong. Because if Einstein had stuck to his original idea, he could have been famous. But instead, he decided, no, I must be wrong. If we look at the cosmic pie of what the universe seems to be made of, it's 95% things we don't understand, 95% dark matter and dark energy. This, we believe, is the composition of the universe. So this illustrates several things. It illustrates, first of all, why chemistry is not important. Only 3/100% of the universe is chemistry, is the chemical elements other than hydrogen and helium. There is more to the universe, more mass in the universe in the form of neutrinos that Dr. Mena studies than in chemistry. Stars are 0.5% of the universe. There is a very difficult to detect gas of hot hydrogen and helium between galaxies. That's 4% of the universe. Dark matter and dark energy are 95% of the universe, and we don't know what it is. 95% of the universe is a mystery. So we can ask, how will we solve this mystery? Well, there are two ways you might imagine solving this mystery of what is the dark matter and dark energy. There is the method of inspiration. This is a top-down method where someone develops the theory of everything. So, for instance, Leon Letterman, there, pictured there with the beard, comes up and discovers the theory of everything and then reaches out and gives a theory of everything that is actually a picture of Joe Lykken, to Joe Lykken, and Joe will know what dark matter and dark energy is. This is the way of inspiration. There's also the way of perspiration to discover the solution to the mystery, where you work very hard, do experiments, develop theories, and don't sit under an apple tree waiting for inspiration. 95% of the universe is mystery. Cosmologists today are no stranger to mystery. But mysteries, I think, are a wonderful part of life. This idea was beautifully expressed by Einstein, who said, "The most beautiful thing we can experience is the mysterious. It is the source of all true art and science. Those to whom this emotion is a stranger, who can no longer pause and wonder and stand wrapped in awe, are as good as dead. Their eyes are closed." In part for his role in answering the cosmic mysteries of 100 years ago, Einstein was named Time's Person of the 20th Century. Perhaps the person of the 21st century will be someone who answers the cosmic question of dark matter and dark energy. So if you want to be the person of the 21st century, I could give you no better advice than to try to understand the nature of dark matter and dark energy. Now, I have no doubt that the questions, the cosmic mysteries of dark matter and dark energy will be answered. We have today, and you will have at your disposal when you try to answer these questions, a remarkable array of accelerators, telescopes, and satellites devoted to this question. But the most remarkable tool at our disposal is the tool of human curiosity and human imagination. Our curiosity, your curiosity, will drive you in ceaseless exploration. Somewhere on Earth today, there is someone with the imagination to reach out and connect the inner space of the quantum and the outer space of the cosmos and complete Einstein's legacy. That, my friends, is your homework assignment. My name is Rocky Kolb. I approve this message. Thank you.
So you've heard some of the really, really big questions. There are even more questions that Rocky could have talked about in cosmology, but now I want to turn a little to particle physics and talk about some big mysteries in particle physics. And then when we get in our discussion, we'll talk a little more about how these mysteries in particle physics are related, we think, to some of these big mysteries in cosmology. So Rocky has already told you about this remarkable connection between the physics of the cosmos, which is the biggest physics we know about, and the physics of the quantum, which is the most microscopic physics that we know about. And that's really a remarkable connection. It's almost unbelievable that there is such a connection. And just to reinforce that for you, to understand physics on ordinary scales, you don't need particle physics, right? If I want to understand why there's bugs in my apartment, particle physics has nothing to say. But it's when you go to much bigger scales, much bigger than ordinary scales, out to the size of the universe, all of a sudden particle physics comes back in. And it comes back in a very essential way. And it works both ways. You need particle physics to understand cosmology, and you need to understand cosmology and what's happening out in the big universe to figure out some of the big mysteries of particle physics. And we've really only begun to appreciate this fact recently, and it's one of the real revolutions in science going on today. So, particle physics. If you want to do particle physics, you need to make particles and study them, or get them from somewhere and look at them. And you need a laboratory for that. And we are fortunate here to live near Fermilab, which is one of the most remarkable laboratories in the world. It is the largest laboratory in the US devoted to just basic science, just to getting knowledge, not to applying it to do this or that, but just to understand the universe. And it also has many other remarkable features. It is at the moment the site of the world's most powerful particle accelerator, the Tevatron, which I'll talk about, show you a little movie of. And it does many other amazing things. This is just one example. It is, Leanne will correct me if I'm wrong, but I think it is the world's largest producer by weight of antimatter. And in fact, we produce antimatter not to power our warp drive engines or anything, but we actually use the antiparticles, antiprotons, the antiparticle of the proton, in our particle experiments. We actually collide antiprotons with protons in order to do our particle physics experiments. So we're using amazing technology to study basic physics. And that's what an antiproton beam looks like, the thing at the bottom there, in case you haven't seen one before. Particle physics is sometimes called high energy physics, and it's because the game here is that you're accelerating elementary particles, like a proton or an electron, to very high energies, and then using that to probe very, very small distances, subatomic distances. And so basically particle accelerators, which is the basic thing we're using, are microscopes. They're the most powerful microscopes we have that can probe the smallest distances by far of any kind of technology. And there's another thing that you do with particle accelerators, which is just as important, which is when you collide particles, you don't just break them up into their pieces. You actually take some of the energy from those collisions and you convert that energy into new particles that weren't there before. So this is E equals mc squared. I can convert energy into matter, and it doesn't have to be the matter I started with. And this is an extremely powerful idea. It allows us to make particles at Fermilab that don't normally exist on the Earth. We can not only make them, but then we can study them. And so it's manufacturing new kinds of matter in the accelerator. And of course, the reason why we need big accelerators is because the more energy you have in the collisions, the more kinds of new particles, exotic kinds of matter that you can produce and study. That's why we need these big machines. So roughly put, you collide two things, the more collision you have, the more you can get out, but what you get out has nothing to do with what went in. In principle, any particle that is allowed by the laws of nature can come out of a collision. So in the real world, that would be very odd, but it's exactly what happens in particle physics. There are many different ways of making a particle accelerator, but the one that works best is the same principle that you see here. Even a little kid can spin up this handy little device to rather high speeds just by hitting it a little every time it goes around. And in fact, if it weren't for friction, even a little kid could spin this fast enough to make everybody else fly off and die. It's a very powerful acceleration mechanism. And that's basically how our most powerful accelerators, including the Tevatron, work. In fact, the earliest example of this device was the original cyclotron that was built by Lawrence and Livingston many, many years ago. This is what it looks like. This is larger than actual size. The actual thing was about 11 inches in diameter. And that was the start, if you like, of particle accelerator physics. And now, of course, we see things that are many, many thousands of times larger. In fact, here is a picture of the Tevatron. You see the Tevatron is the world's largest particle accelerator at the moment. It is underground, so that green line there is showing you where the tunnel is that has the accelerator in it. And it has a bunch of other accelerators that feed into it. You don't get to the highest energies right away. You do it in stages. So there's a whole series of accelerators at Fermilab. One feeds into the other. Every time you do it, you get into higher and higher energies. And then in the end, at the Tevatron, you have high-energy protons going one way and high-energy antiprotons going the other way. And I'm now going to show you a 38-second movie of the Tevatron. So I'm only going to do this once, so pay attention. It goes by pretty fast. So here we are at Fermilab. There's the building where we work. There's people working. They're confused. There's some buffalo. There's a special effect showing you where the Tevatron ring is, but of course it's underground. So now here we are underground. This is the actual tunnel. There's a famous physicist riding a golf cart in violation of safety standards. And those things near the wall on the red things there, those are the superconducting magnets of the actual Tevatron. And inside those magnets is a vacuum pipe, and inside that pipe are protons going one way, antiprotons going the other way. And when they collide, we get the high-energy collisions that I was talking about that allow us to make new kinds of particles. So that's the basic idea, and that's why we have this huge complex of accelerators. Now, once the particles collide, you have to study what happened. And to do that, you need what's called a particle detector. And here's an example of one of the big particle detectors we use at Fermilab. It's called the CDF detector. And those are people, so that gives you an idea of the scale. These are, I think, the largest single most complicated devices that anybody uses for anything. These are packed with electronics and all kinds of high-tech fancy equipment to collect information about what happens when the particles collide. And what you get out of it is pictures like this. And then you have to figure out what that meant. And this is a big challenge. And in fact, you have to figure it out for millions and billions and even trillions, or actually trillions of events that are produced in the Tevatron collisions. And you have to somehow sift through all of that to find the occasional event where you made a new particle that nobody ever saw before. And that's the real challenge of this, is to sift through all this very expensive data and find new physics there. And that's why you have hundreds of physicists working at Fermilab to do that job. Now, actually, it turns out you don't have to be a PhD physicist in order to do this job, and even to do it very well. just by coincidence, yesterday in Fermilab Today, which is our little online newspaper, there was an article honoring 2 IMSA students for their work analyzing real data from the CDF detector that I showed you. And in fact, they were looking for evidence of supersymmetry, which I'm going to talk about in a minute. And they did, as far as I can tell, they did just as good a job as any of the other real physicists did at Fermilab analyzing this data. So I think it's really remarkable. But it just shows you that what's really required is hard work and intelligence, and the rest of it you can learn on the job, basically. So you can get into this particle physics business pretty fast if you're dedicated and motivated. So we have learned a lot, not as much as we'd like, but we've learned a lot about particle physics using accelerators and other kinds of experiments. And this is it in a nutshell, and put on one slide. There are a bunch of elementary particles, and here they are. By my count, there are 57 elementary particles that we know of. That's not including the Higgs boson, which we think is there, but we haven't seen it. And these particles can be divided up into what you call matter particles, things that we're made out of, like quarks, electrons, and force particles, like the photon that carry the basic forces of nature. There are many weird things about this theory. It's a very elegant theory. Basically, you can write down the equations that describe it right there. There it is. So it's a very economical theory. But it has many weird properties, and it also has things that it doesn't even attempt to explain. And the most obvious thing that's missing in this model is gravity. The standard model of particle physics has nothing to say about gravity. So we're in a situation where we've learned a lot about part of the particle physics world, and we're trying to figure out what else is there. And this is a game where you can go very far wrong. You've got half a banana, you're trying to figure out what you're missing. You think, well, I'm missing the other half of the banana, but it often happens in science that the other half is very different from what you were expecting. And that's what we think is probably happening here, that we're going to go from this standard model of particle physics to a bunch of very interesting and new kinds of physics by probing with new experiments. And this is just a list of some of the names of things: supersymmetry, Higgs boson, superstrings, grand unification, extra dimensions. And I'm going to mention a couple of those now. Supersymmetry is one of the hot items that we're looking for right now in experiments at Fermilab and other places. It's a very powerful idea. It basically predicts something dramatic. It predicts that all of the elementary particles we've already seen have what's called a superpartner particle, another particle that goes along with them. So the electron has a partner called the selectron, the photon has a partner called the photino, and that means there's a whole bunch of new particles to go out and discover, which of course particle physicists love. But even more interesting is that supersymmetry gives you a very good idea of what the dark matter that Rocky was talking about could be. So the dark matter is the red slice of the pie there, the blue slice is the dark energy, the yellow slice is everything else. We would like very much to understand what that red slice is, and supersymmetry, if it's right, may be the explanation. It may tell us that the dark matter is actually one of these superpartner particles. In fact, just to give you an idea, there are many different kinds of theories using supersymmetry, and they give you many different possibilities for what the dark matter is, and this just gives you some of the names for some of the things we could be looking for. And these are particles then you can go out and look for. If supersymmetry is right, these particles you can produce them, you can go out and look for them, and by studying them, you should be able to find out whether they're the dark matter. Now, the other thing I said is that the standard model has nothing to say about gravity. And that's a big problem. It's especially a big problem if you look out into the universe, where gravity is very important. For example, many galaxies, I guess most galaxies, have supermassive black holes at their centers. And in fact, here's a picture of 2 galaxies colliding, and they have 2 supermassive black holes in their center. And so that we know that out in nature there are very extreme events happening with gravity right now, and we need a theory to understand that extreme physics. And of course, there were extreme events in the early universe, starting with the Big Bang, that you can't understand unless you have a better understanding of gravity and how gravity can be understood as a quantum theory. So this is a huge thing that we need to understand, and at the moment we know almost nothing about it. there is a candidate theory for quantum gravity called string theory. And this at the moment is a mathematical theory. You can write it down and look at its equations, and you can make animations of what it does. It is a quantum theory of gravity. It's a quantum theory of space-time because gravity is related to space-time and how space-time curves. So if it's right, it's a theory that should tell us about the big mysteries that have to do with space-time and gravity, and maybe other things like dark energy that seem to have something to do with space-time and gravity. So string theory is an extremely important idea. It's also a very radical idea. It's an idea that says that when you get to the most microscopic level, particle physics isn't particles anymore. It's strings. And in fact, those 57 elementary particles that I showed you before in string theory are just 57 different ways that a string can vibrate. So it's an elegant idea. It says there's not a whole bunch of elementary particles. There's one kind of basic thing, superstrings. And they wiggle in different ways, and those wiggles make the whole universe that we see. That's the idea. It's also a very radical idea because of the predictions it makes. It predicts supersymmetry, the thing I just told you about, and it also predicts that space-time has 11 dimensions, by which I mean there's a time dimension and there are 10 spatial dimensions. Now, if you look around, you don't notice 10 spatial dimensions. You notice at most 3 spatial dimensions. So this is a very radical idea. But if string theory is right, if it's the theory of quantum gravity, the extra dimensions have to be there. Another way of saying it is, if string theory is right, this whole view of the universe gets replaced by this, where the whole universe that we've seen is this slice. There are extra dimensions going off in other directions, and there's a whole nother universe of the extra dimensions that we know nothing about because we haven't been able to probe it yet. The extra dimensions, if they're there, affect physics, however. That's the important thing. So this is not just some kind of philosophy. This is real physics. They will have effects on particle physics that we can go out and measure. In fact, we may already have measured them, but we're too stupid to realize that they have something to do with extra dimensions. And that's basically the trick here, is you're trying to understand the connection between extra dimensions and physics that you can measure. The idea that there might be extra dimensions has been around for a long time, and the thing that is really new is we've had better thinking now for why we don't see the extra dimensions. If they're there, something is hiding them. There's a physical mechanism that hides them, and we need to understand what that mechanism is in order to get around it and see the extra dimensions. So there's several explanations. The most obvious explanation is that the extra dimensions are curled up in, say, little circles. If I can move in those directions, but those little directions are tiny microscopic circles, then I don't notice that, or I don't do it in ordinary life because I can't move in those tiny circles. That's a very old idea. It's just the contrast here between the tightrope walker that thinks she's walking on a line and the bug, who's much smaller, that says, no, it's not a line. There's actually a little circle I can go around. But if you're not small enough, you don't notice that that extra dimension is there. Another idea about why we don't see the extra dimensions is called the brain world. This is a much newer idea. And there the idea is that there are extra dimensions, but we can't see them because we can't actually move in those directions, period. We're trapped on what's called a brain, a wall, or a slice in the extra dimensional world. And if that's true, then ordinary matter, at least at ordinary conditions, just doesn't move in those extra directions. And other kinds of matter, or gravity, or something else, does see the extra dimensions. And so you have to use gravity or something else in order to probe the extra dimensions. So gravity, again, becomes the key, because even in this version of hiding extra dimensions, the way you see extra dimensions and understand their physics is by understanding what gravity is doing, because gravity sees all of space and time. Gravity is intimately connected to what space and time is. So sort of the center of everything we're talking about today is gravity. The mysteries of cosmology, mysteries of particle physics, string theory, what it all comes down to is we don't understand gravity, and we think by understanding gravity, we're going to understand many mysteries of the universe, including how I got on a slice of toast there. So we've already seen this slide. It is a puzzle, and what we're trying to do here is solve many different mysteries that are related and solve them by attacking them in many different ways. And particle physics is one of the ways of getting at cosmological puzzles, and cosmology and astrophysics is one of the ways of getting at particle physics puzzles, and we all have to put it all together somehow. And that's going to, as Rocky said, that's going to be a big job, and it's going to take longer and smarter people than me in my career to do it. So this is it's a long road, but I hope we've given you a taste for what some of the exciting ideas are. Thank you.
Okay, we are going to start the discussion. I have a question for you. What about if supersymmetry partners of the particles does not exist? Can you explain more the other additional sources for dark matter, and how can we prove this?
Yes. So one of the embarrassing things about dark matter is that with our great imaginations, we have come up with a very long list of possibilities for what it could be. And only one of them is at least part right, and that is the existence of neutrinos, we now know, because neutrinos have mass, is a part of the dark matter puzzle, but actually it's only a small part. And so most of it is something else. It may be many different kinds of things, but most of it is something else. If it has nothing to do with supersymmetry, it could have something to do with extra dimensions. Extra dimensions, I didn't have time to say this, also predicts the existence of new particles. Some of those new particles can be stable, heavy particles, and they could be out there in the universe making up most of the dark matter. So that could be an explanation. And there are explanations that involve even more exotic heavy particles, for example, WIMPzillas, which Rocky and his collaborators invented, which again are tied to ideas like supersymmetry and string theory, but are examples of really exotic, strange particles, which, if they're out there, could be making up most or part of the dark matter. So there are many possibilities, and that's, of course, why one of the reasons this is a big mystery. It's not that we can't think of anything for the dark matter. It's that there's many possibilities, and now we have to sort them out by doing experiments and observations.
So, Rocky, can you explain more this idea of WIMPs, please?
Of what? Sorry?
WIMPs.
So we don't know what a galaxy is made of. We know it's not, most of the mass of the galaxy is dark. It's not emitting light. So we have yet to detect it except by its gravitational force. So if it is an elementary particle that's yet to be discovered, it interacts with normal matter very weakly. So as you sit here today, the dark matter, the thing that makes up most of the mass of the universe, is passing through your bodies without affecting you. You don't notice it. And it happens not only in Aurora, but no matter where you go in the universe. So the dark matter interacts very weakly. We know it's weakly interacting and massive, and it's a particle. So it's known as a WIMP, a weakly interacting massive particle. That's all we know about it. Its mass, we don't know, the mass of an individual WIMP. We don't know whether it's related to supersymmetry or not. We do know that Fermilab creates primordial soup in the collisions of particles at high energies. If most of the mass of the universe is a WIMP that was produced in the primordial soup of the Big Bang, since we recreate the primordial soup of the Big Bang at Fermilab, we should be able to create a WIMP at Fermilab. So if you go to Fermilab, you want to look for WIMPs.
That's easy.
But possible detections, or
Sorry?
yes, there are projects, right?
There are other ways, other than producing a WIMP at Fermilab, that we may be able to detect and really discover the properties of the mass of the universe. If it's a WIMP, it's passing through you, and you don't notice it because it interacts very weakly, but it should have some very feeble interaction. So it's possible that if you had a very, very sensitive detector, you would be able to detect a WIMP coming through, passing through the Earth, then bumping just one nucleus in this detector and causing it to recoil just a little bit. This is known as direct detection of WIMPs. Now, to do this, you have to have a very sensitive detector, and the detector could not be on the surface of the Earth because we're bombarded by cosmic rays. You have to go someplace to shield the detector from cosmic rays. So what's done is we go around the world looking for mines that are not being used and send our colleagues deep underground. They grow long beards and they become gnomes, but that's all right. And they build very sensitive detectors looking for the WIMP. And Fermilab is operating one now in a mine in a remote part of northern Minnesota. Actually, that's redundant. Every part of northern Minnesota is remote, but so some part of northern Minnesota. And we hope to detect the WIMPs that were produced in the Big Bang in this mine at the same time we're producing them in the collisions at Fermilab. There may also be signals of WIMPs that we can pick up by satellites. WIMPs could collect in the center of the Earth, the center of the sun, or in the center of our galaxy and annihilate, producing very high energy particles that we can detect by satellites. So there are many ways we're looking for dark matter, but we still haven't found it, but it could be any day now. Or it could be another 20 years and you could discover dark matter. I guarantee you a trip to Stockholm if you discover dark matter.
Now, it's your turn. Can you talk a little bit more about string theory? How can we prove, can you explain?
Yeah, so the little vibrating strings, if they're there, are really, 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 really small. And that's a problem because this is supposed to be a scientific theory, so you're supposed to be able to test it. And how do you test it if the fundamental thing you're looking for, which is wiggling strings, are way too small to see, even with our super microscopes, the particle accelerators? What you have to do is you have to say, well, can I figure out what string theory is doing by looking at what kinds of predictions it makes? And I already told you two predictions that string theory makes. It predicts supersymmetry, and it predicts extra dimensions. In fact, it even tells you how many extra dimensions there are. So I think for at least the foreseeable future, the way that you test string theory is you look for supersymmetry, which we can do with particle accelerators and other ways, and you look for extra dimensions. If you see both of those things, well, you're happy anyway, even if you don't like string theory, because you've discovered supersymmetry and extra dimensions. But that sort of clue, I think, would tell us that we're on the right track with string theory.
So the future of our lab can dramatically change, right? Independent. How can, in 10 years from now?
I think, we talk about the future of physics just from the things that we know are going to happen in the next 10 years, both with particle accelerators, underground experiments like Rocky was talking about, things we're doing in space and with telescopes. Just those things that we know are going to happen are going to completely revolutionize the way we think about everything, because we're going to find out that some of these ideas that we're talking about today are wrong, and maybe some of these ideas are right, or maybe they're all wrong and somebody's going to come up with a new idea. But we're going to have data that really gets to the heart of the things we're talking about.
Rocky, can you talk us about gravitational waves, please?
Oh, about gravitational waves.
What are they? Can you explain us?
Yes. It would take 3 hours, but I'll condense it to 3 minutes.
Okay.
So one of the things that was discovered in the 19th century is that if you take an electron or any charged particle and wiggle it around, you produce an electromagnetic wave. And electromagnetic waves we see all the time. It's light is an example of electromagnetic waves, a radio wave, radar. It's all produced by wiggling charged particles around. Because electromagnetic waves are the force carriers of charged particles. Now, one of the consequences of Einstein's theory of relativity is that if you take a mass, say if you take the Earth, and you wiggle it up and down, you don't produce anything. You don't produce gravitational waves. But if you take the Earth and squish it and deform it in one direction, don't try this at home, but if you squish and deform the Earth in one direction and then squish it and pull it in the other direction, you produce gravitational waves. Now, we think that throughout the universe there are gravitational waves that are just passing every place in the universe that are produced in the collapse of stars, in the explosion of stars. There are black holes we know in the universe. We've discovered black holes orbiting about other black holes. 10 million solar mass black hole orbiting about another 10 million solar mass black hole. We know the galaxy that it's in. We know that in 12 million years next Tuesday, these black holes are going to coalesce, they're going to collide and produce a tremendous amount of gravitational waves. We believe this is happening everywhere in the universe. We've detected electromagnetic waves. We have yet to detect a gravitational wave. There are experiments on Earth, 5 or 6 of them in various parts of the Earth, 2 of them in the US, one in Louisiana and one in Washington, the state of Washington, that will detect in the next few years gravitational waves produced by some cosmic cataclysmic event, like the in-spiral and collision of black holes. We will also, in the year 2013, the launch will be on a Tuesday again, going to launch a satellite called LISA that will look for gravitational waves by having satellites separated by 5 million miles. And when a gravitational waves pass through, these 3 satellites will have their relative positions distorted by a few fractions of a millimeter. And that will be a great detection of gravitational waves. In the future, if you become an astronomer, gravitational wave astronomy will be one of the forefront areas of astronomy. So it's a new window to the universe that's going to be opening in the next few years. And if you're interested in astronomy, you may get the opportunity to take advantage of it.
Yeah, let me add, I mean, it's something to think about when in the future of this field is that this idea of new windows. So one of the reasons why we have a big revolution in cosmology is because people finally figured out how to make telescopes that see in things other than visible light. And so they look in radio waves, you look in X-rays, you look in gamma rays. And because you have now all these different windows, you see a lot more things than you could see before. And now we're looking forward to opening yet more windows, looking at the universe in gravity waves. And if you're thinking about, doing something in science, that's a great way to think about it, is to look at what are the new windows going to be, because that's the place where the big excitement is going to happen in the future, is places where people have just never looked before because they didn't know how to look.
It's seeing the universe with new eyes. You want to ask some questions from the audience?
Yes. I suppose you have a lot of questions, and you are for sure very, very welcome to participate.
Questions about anything in the universe. Easy questions.
Except cockroaches.
Dave Workman, teacher at IMSA. What does the theory say about the speed of propagation of gravity waves?
According to Einstein's theory of relativity, the gravitational wave should propagate with the velocity of light. It is yet to be demonstrated that they propagate with the velocity of light. This will be an interesting experiment that will be done once we have LISA, this gravitational wave antenna in space. LISA will be able to look just about anywhere in the universe and say, there's going to be the collision of a black hole at this region of space sometime next week. And you can point your telescopes there, and as you detect the gravitational waves, you can detect the light and see if there's any time difference in the propagation of gravitational waves and the propagation of light. It will be a great experiment and a fundamental discovery. If it doesn't propagate with the velocity of light, then Einstein was not wrong, but he was incomplete. We know, as Joe talked about, that Einstein's theory of gravity is a fundamental discovery, but it's not the final answer. It's not the final word. There is no quantum theory of gravity, for instance. And one of the most important fields of research now and in the near future will be to try to understand gravity, this feeble force. Everyone thinks they understand gravity, but we really don't.
People have even proposed models with extra dimensions where you see gravity waves seeming to go faster than the speed of light. And it's basically because they take a shortcut through the extra dimensions. So in some sense, they go the speed of light, but they go the shortcut way to get here. And so they will seem to go faster than the speed of light.
Hi, Bob Razzle. What determines the wavelength of a gravitational wave, or what moderates it?
Okay, the question is, what determines the wavelength of a gravitational wave? It's basically the size of the system that's producing the gravitational waves. So if you have two stars that are colliding, then it produces gravitational waves of several wavelengths, but the dominant power will be emitted in a wavelength about the size of the stars that are colliding. So if you have black holes colliding, it would be about the size of the black hole is the best place to look. If you have gravitational waves that are produced by the collapse of a star, producing an explosion known as a supernova, then that would be the size that you want to look for. It produces a spectrum, different wavelengths, but that's most of the power is emitted on a size of the scale of the system.
Hello, I'm Paul, a student. I have a question that you were talking earlier about how dark matter could exist in our solar system right now and on this planet in Aurora.
I have some in my pocket.
All right. If that is the case, and you say that dark matter makes up for about dark matter and dark energy makes up for about 95% of the universe, and predicts that galaxies are actually more massive than they are, then wouldn't that predict that the solar system is actually more massive than it is, and we have theories, Newton's force equation for gravity and stuff like that, to predict the mass of the sun and the planets and the orbits? Wouldn't that screw up the mathematics in there, and couldn't dark matter just instead be a very massive black hole?
Yeah, those are all very good questions. The answer is yes. Dark matter since it interacts so weakly, it doesn't, we don't know anything about it, so what we believe is that it doesn't stick together to form dense objects like planets and pizza and things like that, right? So it doesn't stick together to form dense things. That it is a gas, it's like a dark matter gas we are embedded in. And at our point in the galaxy, we're about 15 or 16,000 light years from the center of the galaxy. And at our point in the galaxy, there's about the same amount of dark matter at our point than there is the mass in stars and planets and things. If you go out farther than from the center of our galaxy than we are, then dark matter dominates. So the dark matter density around us is not larger than the density of stars. And in the solar system, it's not larger than the mass of the sun, but it still has an effect, and people are trying to work out some precision way to look for the effects just as you demonstrate. Probably the most promising thing to do is look at the dynamics of a galaxy to see the effect of dark matter rather than the dynamics of an individual stellar system. So around us there's dark matter, but the dark matter density around us is smaller than normal matter, because we don't live in a typical place in the galaxy. We live around a solar system. There is much more space in the galaxy than there is stars, and the space is full of dark matter.
I'm Gabe, Paul's roommate. What are some of the implications for extra dimensions?
some of the implications? Well, we talk about a couple of them. One is, if there really are extra dimensions, then the universe is a lot bigger than we thought. And so, of course, that means you have to rethink all of cosmology. It means everybody that ever was doing cosmology was doing the wrong problem because they were using a universe that was much too small. It probably is going to tell us something profound about gravity, and we've already mentioned that, but we don't know what it's going to tell us. What tends to happen in theories with extra dimensions is that gravity can be much stronger than we thought. Gravity on the Earth, it may seem pretty strong, but it's actually a very weak force compared to the other fundamental forces. But in theories of extra dimensions, you can create a situation where gravity is much stronger than it normally is. And that's a very exciting idea, and there could be many interesting ramifications of having strong gravity around.
Hi, I remember reading something about a theory of multiverses and how other universes could be abundant with other particles that we consider exotic. So could you elaborate more on that? Thanks.
Yes.
Who's going to slide?
Could I have my slide on? Or? Could I have this on, please? I have multiverses on my computer. Maybe I have to do something.
Today only.
Well, if you hang around during the breakout session, I will show you a multiverse. So the question is about multiverses. So let me back up a little bit. 100 years ago, if I was here at IMSA talking about the universe, I would tell you the universe is about 30,000, thank you, is about 30,000 light years in diameter and contains about 10 billion stars. In other words, it was thought that the entire universe is just our galaxy. That was 100 years ago. Then it was discovered by Edwin Hubble that in fact these distant fuzzy things are galaxies, island universes just like our own galaxy, and greatly extended our perception of the size of the universe. Now, in many theories of cosmology, theories of the early universe, lead to the prediction that the universe that we see, that stretches out for billions and billions and billions of miles, is only a small part of a vast network. And what we're seeing is our universe is just part of, there are other universes, and this entire thing is called a megaverse or a multiverse. And in this picture, we live in one of these bubbles in this universe, but there are other universes where, in fact, might have different numbers of dimensions. The laws of nature might be different, or it might be identical to our universe. This seems to be an inescapable consequence of theories of the early universe. We don't yet know how to detect other universes or how to see them, because it would be the same problem that we face in trying to answer the question, what is inside of a black hole? There is a horizon that prevents us from seeing inside of a black hole. There are horizons, and the space is so distorted that we cannot see into other universes. But we may discover one day how to explore and see other universes. So it's one of the exciting possibilities that we are at a complete loss about how to make use of this, how to discover them, but the theories predict that they're there. Now, theories predict much more than is ever discovered. There are many more theories than possible outcomes of nature. So we don't know whether there are other multiverses. Some clever person has to figure out a way to see into a multiverse, to see into another universe and discover the multiverse. And perhaps we'll take a step just like we took 100 years ago, extending what we believe to be the size of what's out there.
Hi, Dr. Lykken. Earlier you mentioned, kind of in passing, that like neutrinos have mass, but this wasn't something that was always believed to be true, right?
That's right.
And I don't know, so it's generally accepted now that the neutrinos do indeed have mass. And I was just wondering, first of all, when exactly did this happen? Because I mean, this is pretty recent.
I'm going to let Dr. Mena answer that question because she is the expert on neutrinos.
Oh, it's not. How can it happen? Can you repeat the question, please? How can it happen that the neutrino has mass?
Well, I was just wondering what exactly changed the scientists' outlook
Ah,
How did
to
we
make them
figure it
believe
out?
that it does
Yes.
have mass now.
Yes.
How do you know neutrinos have mass?
Is it all connected to the dark matter?
yes. In principle, there exists no reason not to accept a mass for a neutrino within the model, which now, out of this model, excuse me. Within this model, it's not possible to have a term or a massive neutrino, okay? Because there not exists the kind of particle which normally is connected with another particle in a term in a big, in a big math tool that we use to explain the interactions between particles, okay? So then what happens is that neutrinos from an initial certain flavor, you know what flavor, we have three generations of families, and there are three different, up to now, there are three different neutrinos with three different flavors. So if the neutrinos are massive, they cannot change, are not massive, they cannot change its flavor, okay? So if a neutrino is born or in the source initially is a neutrino of a certain flavor, E, for instance, which is the partner of the electron, okay, has to be detected with the same flavor, okay? If neutrinos are massive, quantum phenomena, which are oscillations during the way from the source to the detector, make it to change flavor, okay? Because there is a mixing between the massive neutrinos, okay? And then we notice that the neutrino is detected with a different flavor, and it indicates that it has mass. Does it answer your?
I'll give you
Also, sorry.
I was going to give you an example of how we do this in the experiment. We see neutrinos coming from the sun, for example. The sun produces neutrinos as a result of the fusion that powers the sun. And we think we understand that fusion, and we think it only produces one of these three kinds of neutrinos. So we look at the neutrinos coming from the sun, we expect them to be all of this one type, and instead we find that they're a mixture about roughly equal of the three different types. So somehow, in between getting produced in the fusion in the sun and getting to the Earth, one type of neutrino turned into another type of neutrino. And we think that is related to the fact that they have mass. So that's the way you figure out that neutrinos have mass.
Also,
Okay.
you were talking about the Higgs boson, which hasn't actually been detected, but
Right.
like I know like CERN is opening up something in a couple of years
Yes.
that's supposed to detect this for sure. I don't know, or I mean, it's believed that this is going to give them a really good chance to detect this. Now, I'm just wondering, what's the significance behind the Higgs boson that makes it like so that everyone's so eagerly anticipating the evidence?
You're absolutely right. So the Europeans who love physics even more than we do are building an even bigger particle accelerator than Fermilab has, and with the idea of discovering, among other things, the Higgs boson. And the reason we're so anxious to find that particle is because that particle seems to be related to a whole bunch of different mysteries. One is the mystery of why particles have mass at all, which is something that we don't understand, and also why particles have such different masses. Neutrinos are very light, other particles are very heavy. And it also has to do with why the forces of nature look the way they do, and why we see such a complicated world around us. So the Higgs boson seems to sort of be at the center of a bunch of mysteries of particle physics, and by getting our hands on it and studying it, we think we're going to figure out a lot of these mysteries.
So,
Okay, I got a question. Do you think string theory would explain the loss of magnetic fields in Mars and the decrease of the magnetic field in the Earth? Like,
one of the things people think about with string theory and other theories that talk about new physics is whether they might predict exotic forms of matter which might collect inside planets and do weird things. And so what you're asking is an example of that. And people have actually used this idea to go out and look for evidence of weird kinds of matter by looking for weird effects that of things like the Earth's magnetic field and other kinds of things that you can look for very sensitively. And so far, we haven't found any evidence for exotic matter inside the Earth. But it's still an open question. If there are weird kinds of matter, you would expect them to collect in planets and stars, and maybe there's some stuff at the center of the Earth that we don't know about.
just so you, in case you want to know what neutrinos look like.
Hi, I've heard it said before that the universe has sort of evolved to become very clumpy in nature. And do you think, could you elaborate on how dark matter might change this view and like explain why the universe is so clumpy?
Yeah, that's a good question. So as we look out in space, we're looking back in time because of the finite velocity of light. So as we look farther and farther in space, we're looking further and further back in time. We can look out in space back in time and see the universe 380,000 years after the Bang. Now, we believe the universe is about 13.7 billion years old, so this is really looking at the very early universe. And when we look at the universe 380,000 years after the Bang, we see that matter, that there are no galaxies or planets. The distribution of matter is very smooth. But gravity acts that any small irregularities in the distribution of matter pulls in surrounding matter, and the structures grow with time. So any small irregularities end up growing and growing and growing over the course of time to become galaxies. So the universe starts smooth and becomes lumpier and lumpier and lumpier. However, if there's dark energy in the universe, as we believe, the expansion of the universe is going to be so rapid that the growth of structure is going to shut off, and larger structures than we see now will not form. So that's one of the predictions of dark energy, that 1 billion years from now, the universe will not have larger structures than it has now. It's a definite prediction, and I'm willing to bet Joe's life on it.
Well,
You're not allowed a follow-up question. This is not the League of Women Voters.
Hi, I was wondering if you could say a little bit about supergravity and how that fits into string theory and the theory of everything.
Thank you, Sasha, for asking that. So I said that gravity is the key to many of these mysteries, and I also said that supersymmetry was a very basic idea for new physics coming from string theory. You can combine those two ideas and make a theory called supergravity. And supergravity also makes some amazing predictions. For example, supergravity predicts that gravity is a more complicated force than we've been thinking about, and there's a component to gravity that's anti-gravity. So unlike our usual picture for gravity where everything attracts everything else, if supergravity is right, you can have an extra component to gravity where sometimes things repel through gravitational-like forces. So this idea of supergravity is again something we want to test by looking at its predictions for new particles, and if it's right, it could have very interesting basic predictions about how gravity works.
This is sort of how science works. So theorists come up with crazy ideas, and then experimentalists are gullible enough to believe them. So they go off and spend 10 years of their life doing an experiment to try to test this, and then they come back all excited and say, aha, I proved that you're wrong. And then you say, well, I've had a dozen more ideas.
That was last year's idea.
I heard that the growth of the universe is slowing down, and eventually that it will just collapse into a big crunch. Is this true, and what would be the cause of this?
Okay. We believe, in fact, that the expansion of the universe is not slowing down, but that the expansion of the universe is speeding up. And this is one of the evidences for dark energy. So we thought there were several possible futures of the universe, that the universe would expand and slow down and reach a maximum size and then recollapse into a big crunch. Or that the universe would expand, slowing and slowing and slowing in the infinite future approaching zero velocity. What seems to be the case is something that's strange and was surprising, is that the universe is expanding at an ever-increasing rate. It's accelerating in the expansion, and this is driven by this mysterious dark energy. So if the dark energy does not go away, if the dark energy persists, then the universe will expand faster and faster. And the galaxies we see now eventually will expand so fast, we won't be able to see them, and our galaxy would be the only galaxy in the universe. That's why we want to do astronomy now, because billions of years ago, from now, there won't be anything to see. So we think the universe will expand forever, but my colleagues have been wrong before.
What are some of the proposed ways to test for extra dimensions?
So extra dimensions, there are many different theories for extra dimensions, but one thing they all have in common is they predict new particles, which is good for particle physics because that's what we know how to look for. And another thing that extra dimensions predict is that some particles, if you give them a big enough kick, may actually disappear by moving off into the extra dimensions. So actually the simplest experiment you can do at a particle accelerator for look to extra dimensions is you smash a proton and antiproton, say at the tevatron, and you look at what comes out, and then you balance the energy and the momentum to see if you accounted for everything, and you look for particles that have disappeared. And if they have disappeared, that doesn't necessarily mean they disappeared into an extra dimension, but then you can start to narrow down what are the reasons why you didn't see these particles. You may not have seen them because they were neutrinos, and neutrinos are hard to see, but that's physics that we understand. So by a process of elimination, you might actually be able to prove that by giving a particle enough of a kick, you can actually kick it off into the extra dimension.
In your string theory, you said the basis of string theory was that everything was subatomic strings vibrating in different ways. Does that allow for matter switching, matter changing into other matter, or is that even feasible?
Yes. So as you might expect, if all the different particles that we're made out of are actually different vibrations of the same string, you might imagine that I can actually convert one into the other. And that is one of the predictions of string theory, is that there's words called grand unification. This is even more grand than grand unification. It's the ultimate unification where every kind of particle can turn into every other kind of particle, because after all, they really are the same thing. They're strings, and they're just different vibrations of the string. So again, that's something we can try and test. One of the ways you try and test that is you look for very rare processes that aren't supposed to happen. For example, protons, which we're made out of, are supposed to be stable particles. They're not supposed to be able to change into other particles. And to a good approximation, that's true, because we're all here and we're not unstable. But we are doing very, very sensitive underground experiments where you basically take a big tank of water, you put it underground so you don't have to worry about radiation, and then you look to see if one proton in that whole tank of millions of gallons of water decays and turns into some other kind of particle. And that would be a hint that these ideas from string theory are right.
You said earlier that the reason for looking for dark matter is that the gravitational force in a galaxy isn't sufficient to hold it together. But what's to say that that difference isn't a discrepancy because of our ideas about gravity and not an idea about matter?
That's a great question. And in fact, people have come up with the idea that there's not dark matter, but what it actually is something that's known as modified Newtonian dynamics, that somehow Newton's law of gravity, that the force is proportional to 1 over the distance squared, fails if you go on sizes that are thousands, tens of thousands, and hundreds of thousands of light years. That, it's possible. There seems to be no way that that idea fits into our ideas of modern physics, though. We believe that Newton's laws are modified for very large velocities, very intense gravitational fields, or very small distances. But for small velocities, for weak gravitational fields, and at large distances, we expect Newton's laws to work. However, it's an experimental question, and people are trying to look for an observational departure of Newton's law of gravity on the scales of things like galaxies. So it's a good question, and it's a possibility that can't be dismissed. But I think, in fact, a more conservative interpretation is that there is dark matter.
Will you please join me in thanking our stellar panel?